All right. My name is Ron Diamond. I'm a developer based here in LA. I do software development, consulting, architecture, some UX and other stuff, but primarily I specialize in iOS, native iOS, iPhone and iPad apps. But version control is applicable to all of us using any kind of programming language. So our goal here today is to understand Git conceptually and look underneath the hood and get a much better appreciation of what it is and how it works. So I want to tell you a little bit about the history of Git. It was created back in 2005 by Linus Torvalds. He is, as you may know, the creator of Linux. Right? In the early history of Linux, the guys who were developing and maintaining it, they actually used to email patches around to keep each other up to date on the latest code base. Linus hated CVS, concurrent versioning system, and Subversion, but in 2002 he started using a commercial version control system called BitKeeper by a company called BitMover. At the time it was free for open source projects. It was still a controversial move, though, because they were using what was really commercial software on an open source project. And then, sure enough, in 2005, the maker of BitKeeper started charging for the use of it, even for open source. And so Linus went heads down, and in just a few weeks, he cranked out the very first version of Git. So what is it that he created, and why has it gotten to be so popular? That's really what we're looking at today. And so I became convinced fairly early on that there's kind of a right way and a wrong way to go about learning something like Git. And so a lot of people, they would just sort of jump into the terminal and start typing commands. I'm convinced that that's the wrong way, and so we're not going to do that. Because conceptually, it's different from what came before it. It's different from Subversion and what you may be used to. So we're going to take a different approach, more of a right brain approach, if you will, so that we really get what's going on. And then a little bit later, we're going to get in there and get our hands dirty so you can really see what's going on underneath the hood. And so in order to explain that, I thought we'd try something a little bit different. I wanted to try this sort of Khan Academy style, because right now we're focusing on concepts. So the question that we're asking here really is, why Git? In my mind, there are two major advantages for using Git. There's flexibility and performance. So let's start with flexibility, and we're going to use Subversion as sort of an example. A bunch of you have used Subversion. It's based on kind of a hub and spoke model, kind of like a bicycle wheel. There's one repository on a central server. It has the entire code base along with all the history of that project. And as developers, we share that repository, and we do our work, and then we commit those changes that we've made to this central server, right? So other developers, they update their copies of the repository, of the code base. And then our work is immediately shared, more or less immediately shared with everyone else. So this is simple, it's easy to understand, but it does have some limitations. I actually came to think of this as kind of like working on a chain gang. It's very limiting, there's very little flexibility, because basically all the developers, they're sort of working in lockstep with each other. And anytime anybody makes any changes, everybody else gets them more or less right away. So what if, say, you're doing some refactoring, maybe you're having to break the build in the process, or you're working on a big new feature, and it may not be optimal to have to share those changes immediately. Maybe better to wait until they're ready to be shared, okay? And also, interacting with the repository tends to be slower because we're dealing with this central server and talking to it over the wire. So that's Subversion. Now let's take a look at Git. Git is very different. It's basically a peer-to-peer system. Okay, there is no central repository. That's one of the key differences. Every developer working on the project has his own copy the complete copy of the source code and all the history of the project. And so that actually has an advantage right there because each developer's machine essentially functions as kind of an offsite backup. And when you do a commit, you're actually doing it on your local machine. That's another key difference because you have a full repository on your machine. So you don't have to share those changes right away. You can work in parallel and then share your work when it makes sense to do that. But we still want to be able to collaborate with other people, of course. Because it's peer-to-peer, if you wanted to, you could actually set it up so that you could push changes to your fellow developer's machine directly, if you were set up to do that. And then they could push changes back. That's a perfectly valid workflow. But let's say that you're working days and I'm working nights, and then late at night I go to push some changes to your machine. You may have shut down your machine for the night. So even though you can do this, practically speaking, people have chosen to use an external endpoint just for convenience. Okay, that could be within the firewall or within the cloud. It could be hosted on a service like github.com or Bitbucket or something like that. And so you don't have to do it this way, but it tends to be more convenient. It is just a peer, just like any of the others, and we all share a complete copy of the project with its history. And of course, one of the advantages of using one of these cloud services, let's say, or an external server, is that it's running 24/7. So you can push and pull stuff to it when you want to share what you've done and not have to worry about the machine having been turned off. So the only reason this is special is because we've agreed to use that endpoint to share our work with each other. But it's still just another peer on what's essentially sort of a mesh network. So now, let's take another view of this. We're going to look at sort of a timeline view of what happens in a normal project working within a team. And so we're going to look at the operations that we do with Git over time. So within a team, let's say that I'm over here, and I start a project in my IDE, and then I create a repository, a Git repository, which the IDE may do for me, and I do what's called an init. So in my working directory where I want to be tracking those changes, I initialize a fresh brand new repository, and then I make some changes to what's in that working directory, and then I do a commit. And actually, I could be doing a whole series of commits. Maybe this was a feature, a class that I'm starting to build out. Then I go and I do, say, a bug fix or something, and then I go work on a different class. Maybe I'm working on the data layer or something like that. And I do a series of commits, logical change sets. Basically, I'm making changes to the code base, and whenever it makes sense, when we do a commit, we're saying, okay, I made these changes for a particular reason, and here's the reason, and we give it a commit message. And again, bear in mind, all of this happens on my local machine because I have a complete repository with history on my local machine. Okay? Now, this series of successive commits, it's kind of a history, it's a timeline, sort of a trail of breadcrumbs you can go back and look at if you need to. And this is called a branch. Now, in Subversion, a branch is kind of a special thing that you use once in a while. In Git, you're always on a branch. And the default name for the initial branch is master. That's just the convention. Now, there are actually other more sophisticated workflows. There's something called Git flow, which uses different branches and different naming conventions. We're not going to worry about that for right now. But just keep in mind, when we talk about a branch, we're talking about a sort of chronological history of changes that were made to these files. So let's say we've got another developer working on the project. Okay, so here's Joe. And he's on his machine. And I've started out the project already. I could have been working on it that day or for a week or a month or something. I've got a series of commits. And so we've decided that we're going to use one of these cloud solutions, let's say, or a server within the firewall, depending. And we set that up. The nickname for that, the default name, is origin. So that's the origin server. And again, bear in mind, it's just a peer that we can push and pull things to. And so I want to share my work with Joe. And so I push what I've done to that origin server. So not only does the current state of what I'm working on, the current state of the working directory get pushed, but all of the history of the changes actually get pushed as well along with it. And so the server has a complete history of all the change sets that I've made. So Joe comes in and he says, oh, okay, well, I want to grab that project, and he does what's called a clone operation. And he grabs that and downloads it to his local machine, and now he has this whole history of the project, all of these change sets and everything. So he can go back and look at how the project has progressed if he needs to. Okay, now let's take this one step further. So Joe is going to do some work, and so he goes along, he makes some changes, he's working on a different section of the code, and he does a commit. He says, hey, I made these changes for this reason, and he wants to share those with me, and he pushes those back to that origin server, and then I can pull those down. And in fact, we can kind of work in tandem, we're working in parallel. Maybe I'm on a plane, and I want to do some work while I'm on the plane, and I don't have connectivity, so I can keep working and doing commits while I'm on that plane or commuter train or whatever it is. And then when I get connectivity back, when I decide I want to share that work, again, I can push that, and Joe can push his. And if more than one person has made changes, then there's an operation called a merge. And normally it's automatic. If we've been working in the same sections of code, there could be a conflict and you have to sort that out. But basically the idea is we can be working in parallel because we each have our own repository, and periodically we sync up and share those changes with other people. So let's take this one step further. Let's say that this is actually an open source project and we've posted it on GitHub, and so Susan out here sees this project and she says, hey, that's really cool, I'm going to grab a copy of that. So she grabs a copy of that repository, and again, she's got the entire history of it on her local machine, and she's poking around in there and she says, oh, I found a bug. And so she makes a change and then she does a commit. Okay, we're off working back here. We have no idea that she's doing it. She's done this on her own. But she may say to us, hey guys, you know, I fixed this bug for you, I made these enhancements or whatever it is. And so she files what's called a pull request, which basically says to us, hey guys, I made some changes and you may want to pull those back in to your main repository, say in this case on GitHub. And if we do that, that then becomes part of the history as well.
So the pull request is because she doesn't have permissions to commit it?
Yeah, well, in this case, we're actually pulling those changes. So, I mean, if she had permissions, she could push them. But if she's just kind of off somewhere, really the point of it is that you can collaborate with people that you don't even know are working on the project, and sort of bring in those changes afterwards. And this is one of the reasons I think that open source has taken off, because as you can probably see, a distributed version control system like Git, which is what this is because we all have our own repositories on our local machine, it's actually extremely flexible. You can make it as simple or as sophisticated as you want to. And so it really lends itself to open source. If you've got this repository posted somewhere, somebody can just grab a copy of it and make changes and start contributing. You're actually going to see that in a minute. So let me show you, I actually pulled down a repository off of the web. I went on to GitHub, I pulled down a repo. Some of you may recognize this actually. This is the open source repository for jQuery. And if we take a look at this, and actually here's the working directory for this, and it's got like 200 different files in it. And so these are source code files, right? Another thing to keep in mind about version control is that it actually doesn't care what's in this working directory. We're software developers, so we're working with code bases, source code, but it could really be anything. The version control system doesn't care. This could be letters to your mom. if you were a UI UX designer, it could be graphic assets and keeping track of different versions of those. What the version control system knows is that it's been tasked with keeping track of changes to any of the files that are in this directory, and then it takes a snapshot of it. When we say commit, it goes in, takes a snapshot of the current state, and files that away. And we're actually going to look at how it does that. So yes, it's source code. It doesn't have to be. It could really be anything. But in this case, we've got this open source project. And if we roll this back, the latest commit was made just the other day, less than a week ago. And you can see the entire history of the project. And this entire history is right here on my local machine. And this project goes back quite a ways to 2006. So this over 8 years of work in this repository. It's got over 200 source files. And also, if you can see down here, there's over 6,000 commits in this one particular project. There was one other thing I was going to show you here. If we go back to our little diagram here, I'm going to zoom out, and let's look at this a little bit differently. I'm going to turn this 90 degrees so that time, instead of going from left to right, it's now going from bottom to top. And we'll go back to our open source project here. And if we look back in the history of the project, so again, earlier is at the bottom and later is at the top, and that's typically how you would see this history. If we scroll back here, we see there's a whole series of commits by different people, but this is a long project and different people have been working on it. And so if we look back, over here on the left, you can see how things are kind of splitting off a little bit, right? And this is what we were just talking about, where people have their own repositories on their own machines, and so they can actually work independently. And so we're going back earlier in the history of the repo. That's exactly what we're seeing right here. So these 5 or 6 or 7 different people actually have a copy of the repository at this point in time. And then they go off, and they each made little changes on their own, right? If we follow this forward, these people each made different changes, and then they contributed them back. They pushed them back to that origin server. And so you can see that things kind of diverge, and they converge again. And so there's a sort of ebb and flow. We kind of alluded to this down here, where things are sort of waxing and waning. This is normal in Git. In Subversion, if we take a look at a sample Subversion repository, now I don't even have Subversion software on my machine anymore, so this is a screenshot, but this will give you an idea. It's a very linear process because there's only one repository and you push your changes, other people get those changes, and so as we said, it's really in lockstep. It's a very linear kind of regimented process. So when we look at the history of this repository, this is exactly what we see, is we see people going off, working on their own for a little bit, and then when it makes sense to share those changes with each other, that's what they do. And so, again, it's here, it sort of diverges and then converges again, and that's perfectly normal with Git because, again, we have this peer-to-peer system where periodically we sync up and share our changes. Okay, so now I want to talk about, we said that there were 2 big advantages to working with Git. And let's call up the working directory over here. We said that one was flexibility. We've talked about that. The other is performance. This repository, as I said, this is 8 years worth of work. There's over 6,000 commits here. So let's say that we needed to go back and look at a previous version of this project, this code base. And I'm going to roll this back here just sort of arbitrarily. We could be looking at an earlier release version, or just we want to compare something the way it was done. So let's just pick a commit, that right there, and we say, I want to check out those changes and see how the code base was at that point. This is actually, I just sort of picked this. This is about 5 years ago. And so if we tried to do this in Subversion, again, I haven't done it for a few years, but if you told it, hey, check out that commit, you'd probably need to go out for a coffee break. And if I remember, it may even need to be like a lunch break. because it's going to sit there and kind of chew on it. Don't forget that it's talking to this central repository over the wire, and so there's a lot of transacting that's going on there. But in Git, let's see how long this operation takes. So again, bear in mind, this is our working directory over here. I'm going to leave that up on the screen there so you can actually see what it's doing as it's doing it. And then I'm going to go over here, and I'm going to check out this commit. Again, this is from about 5 years ago. We're going to roll back this code base by about 4,000 commits. Anybody have a stopwatch? We're going to time this. So ready, and oh, that's it.
Okay.
So I don't know if you saw that. If you blinked, you probably missed it. We just rolled back our entire working directory, which is right over here, about 5 years and about 4,000 commits worth. And it did it in about a second. And there's about 200 some odd files in this project. The kind of projects that you and I work on, it would be able to do that operation in a second or a couple of seconds maybe. If it were a big project, it might take 3 or 5 seconds. So obviously there's something different going on here. Git, I would say, is very performant. It is fast. It is like blazing fast. And we're going to dive into this and see why that is. But as you can see, it's already very flexible in terms of just jumping back and forth and making changes. The other thing I want to point out here real quickly is that, I don't know if you can see this, but we're in a mode right now that they call detached head. That's a little bit more of a workflow thing, but I'm just going to mention very quickly. Detached head means that we've gone back in time, basically. We've checked out a commit, and we can look at the code, right? So here's some code. This is the version of this file from 5 years ago, that commit at the time that snapshot was taken. And so we can poke around and look at it all we want to. That detached head, what that means is that because we went back in time, if we actually wanted to start making changes from this point, we would need to create a new timeline. And a timeline in Git terminology is a branch. So we could do that. We could create another branch. So let's say that this were an earlier release version and we needed to do a patch for it, a hotfix. We could go back and make a branch, and that would be the hotfix branch, and that would have its own little history from this point forward. So just a little footnote in case you were wondering. But what I really wanted to show you was performance here. So Git is obviously very different from Subversion, how it works. I want to show you how that is, and we'll start sort of conceptually. So here's Subversion, and so we're writing some code, we're working on some different files. So let's say that this is a file in our code base. It could be, a few or 100 or 1,000 lines. And so I actually want to illustrate this a little bit differently, a little more sort of pictorially. I hope you see what I'm doing here in a second. I'm going to use sort of a pictogram. Let's say that this is what we're working on. This is the current state of this file that we're working on, okay? And we tell Subversion, hey, Subversion, I want to do a commit, so grab a snapshot of that file. And so what Subversion does is the first time a file is committed to the repository, which is actually in a hidden directory, inside your working folder, it grabs what it calls the base version of that file. So we continue on, we're working on our source code, and we make some additions to that source code. So we've got a bunch of lines of code. Really what we're talking about is making changes to a file. But again, this is sort of an illustration. And then we say to Subversion, okay, hey, I've finished this other amount of work, grab a snapshot of that. And so what Subversion does is it actually just grabs the changes to that file, not the whole file, okay? Subversion was created about 15 years ago, and if you think back about 15 years, disk space was at much more of a premium than it is now. Now we don't worry about it so much because hard drives, storage devices are a lot bigger. Let me just take this a couple of steps forward so you can continue to see where this goes. Again, I'm using sort of an illustration. So I make some changes to that file. So again, this is a file in a code base. But I go in and make a couple of changes, and I say to Subversion, hey, grab a snapshot of that. I want to do a commit. And so again, it just grabs the changes to that file, not everything that stayed the same. And we'll just take this one more step, just for sake of completion. So I add some more stuff to that file. I add some more lines of code, let's say. And I say to Subversion, grab those for me. And again, it just grabs the changes to that file. So really just the lines of code that have changed. And so what we're talking about here is that Subversion is really grabbing deltas from one version of a file to another. It's a form of delta compression. It grabs those deltas and it socks it away internally. There's a .svn directory inside your working folder, actually a whole bunch of them. And it stores away these little bits and pieces that have changed over time. As we said, it's basically designed to optimize for disk space. So you kind of get the idea there. We're really talking about lines in a source code file. So now let's take a look at how Git does this. It works a little bit differently. So let's say we do the same thing. We're working on our source code. We've got 100 or 1,000 lines of code in this file. I'm going to use the same metaphor here. So I've got an initial version of what's in this file, and I say to Git, hey, grab a copy of that file because I want to do a commit. I want to snapshot what's in the working directory at that point, and it grabs that file, the whole contents of that file. And so that I come along here and I make some more changes. I've added a few lines of code. And I say to Git, hey, I've made these changes. Why don't you commit those and keep track of the current state of that file? So Git grabs a complete copy of the entire file. It doesn't do any of this delta stuff. And so what that means is you may have a file of source code. It's got 1,000 lines of code, right? You make one little change, one character, one line in that file. It grabs the entire file from scratch. So it'll sock away a copy of that entire 1,000 lines of code, all right? And so let's just take this a little further, our little metaphor. So we make some more changes to the file. Again, this is, a source code file. And we say commit because we want to track those changes. And so again, Git grabs a copy of the entire file. Now, you're saying to yourself, well, wow, doesn't that kind of waste disk space? And so the way I think of this is that Subversion, because it was created, say, 15 years ago, it was really designed to optimize for minimal use of disk space. But we've come a little way since then. The way I think of it is Git was really designed fundamentally to optimize your time. Not disk space per se, although it does do that. We're actually going to see some of that. It does have strategies for compressing files and saving disk space. But first and foremost, it's designed for performance. And so if we go to our final version of the file here, so I've made some other changes just to kind of finish this off. I say commit this file, and Git, again, commits the entire file to this internal object store that it has. And we're actually going to look at that and see how that works. And that actually explains why Subversion is a lot slower, because if you think about it, this delta compression approach really doesn't scale very well. So the project that we were just looking at, we've got 6,000 commits with over 200 files, okay? That's not an unreasonable number of changes for a project that's been going on for a while. And so what Subversion has to do is we say we want to roll it back. And so what it does is it has to reassemble the version of that file from all these little bits and pieces. It kind of goes back to the beginning and says, okay, well, we need to add this and subtract this and change this and so on, like thousands of times in our case. And also don't forget that we're talking about hundreds of individual files, right? So it has to go through this whole process for all those files. So the bigger your code base gets and the more commits that you add to that timeline, the slower it gets, because this delta thing just doesn't scale very well. With Git, it doesn't care. It just grabs a brand new copy of the file that's changed, regardless of how little or how much it has changed, and it socks it away in its object store. The other thing to keep in mind is that Subversion is actually doing a lot of transacting over the wire. Remember, we've got one repository that's on a central server, and so it's doing a whole lot of talking to the server to figure all this out, and that's another reason that it's a lot slower. Okay, so the next thing I wanted to show you is if we go back to our little snapshot of Subversion here, this is a picture of a little piece of the history of a Subversion project. If you needed to refer to a particular commit, say you're writing up a bug report or that sort of thing, you need to have a way to uniquely identify each of these commits. And in Subversion, it's very simple. Because it's such a simple, linear, kind of regimented process, it just numbers them sequentially, right? The first commit is revision 1, and then revision 2, and revision 3. We've only got one repository, and everybody's working with that. So you can number these sequentially, and that works fine. It's a linear process. Go back here to our sample project from Git, and we've got all these people, they're working on their own machines. They each have their own copies of their repositories. And in our example where somebody was off on the web somewhere making changes to this open source project, we don't even know that they're making changes. So people are working independently in parallel, so you can't really number these changes sequentially, because when they come back and share their work, we'd have collisions in those numbers. So we need another way to identify these commits to avoid duplicating numbers. So we need a different strategy for that. So I'm going to go back and check out master. And so this working directory is restored to its current state. And again, that operation took a second or so. So we need another way to uniquely identify these different commits. We're running up a bug report. We need to be able to say, this is the version that I was using at the time and it had this bug, or for whatever other reason. So the way Git identifies commits, it uses a completely different strategy, and it's based on checksums. So when you do a commit, what Git does is it essentially scans the entire contents of the working directory and does a checksum of all of its contents. And that checksum is this guy right here. In the case of Git, it's using a SHA-1 checksum. So that's a fingerprint. It's a unique identifier. Git is using that to uniquely identify these different commits. And so because that checksum incorporates all the state of all the files in the repo, if someone's making changes anywhere in the world to these files and they change anything, that checksum is going to be different. Therefore, it's going to be a unique identifier. And we can use that unique identifier to refer to a particular commit. So in practice, in a given repository, if you need to refer to that, usually just the first 4 or 5 characters will suffice, because that's already thousands of combinations. You just use as many characters as you need. You don't necessarily need to use the whole thing to refer to that commit, but that is its unique identifier. So I said that this is a checksum of the contents of the working directory at this point. But really, it's a checksum of what? And I want to show you, and now we're going to get underneath the hood and start to get our hands dirty. And I think that once you've seen this, you're going to have a much deeper appreciation of what Git really is and how it really works, okay? So somehow we know that this latest commit by this guy Oleg, which was done less than a week ago, it has this identifier. It starts out with 9D6B. And so let's take a look inside our repo. Now, all of these files are source code files, right? This is the stuff that we're actually working with, except for this up here, this .git directory, okay? That's a hidden folder. And what I'm about to show you, feel free to play with this stuff, but do it on a copy of your repository, or just pull something down off of the web, something open source that you don't care about, because this is the inner workings of the version control, and if somehow you mess up the version control itself, you can't use version control to bail you out and undo those changes. Okay, so just sort of a caveat. And so if we go inside here, this is our .git directory, and we can see that it's got a bunch of subfolders. And by the way, this .git directory, this is the actual repository. The rest of it is the copy of our working files that we're dealing with. When we talk about the repository and how you have that on your local machine, that is this .git directory. So we're going to take a look at this folder called objects. We're going to follow a little trail here, okay? The unique identifier starts with 9D in this particular case. So what you see is this objects folder has a bunch of subfolders that are named with 2-digit hexadecimal characters. That's actually the first 2 digits of the checksum that we were talking about. And if I open this up, you'll see there's a whole bunch of files in here. They've got hexadecimal numbers for names and no file extensions. We have no idea what these are. But somewhere in here, I suspect there's something to do with this commit. And so the next set of characters is 6BEA. So let's go back here, 6BEA. And just to double check, it ends with 8E1, and that looks like it. So let's take a look and see what's inside here. We're going to open this up in a text editor. Okay, well, this looks like kind of a dead end. We've just got some garbage in here. But you remember a little while ago I said that Git actually does optimize for disk space. And so what we have here, this is actually a compressed version of that file. Yes, it stored the entire file, but it did a gzip form of compression on it because it's not oblivious to saving disk space. It does have strategies to do that. This is one way that it does that. So it's actually not garbage at all. It's just compressed data. So I'm going to jump back into the terminal here. And again, I don't want you to worry about the syntax or the commands or anything. What I want to show you is, if we grab this number here, this is a unique identifier that somehow identifies this particular commit. We want to see what's going on there. So I'm going to use a Git utility that's in the command line and uncompress that file. And I'm just going to redirect it to a text file so we can take a look at it. Okay, and here's that text file. So let's open that up. Oh, okay, this is starting to look interesting. So what we're looking at here is the commit object. When we said that that's the unique identifier for that commit, what we're actually looking at is it's just a little text file. And it's got some references. It's referring to something called a tree, and that has another unique identifier. That's actually another checksum. It's got something called a parent, DC4B something. If we go back and look at the repository here, we'll see that the commit that immediately preceded this one, so it's saying its parent is DC4B, it knows that because it saw that in this commit object. And that's this commit that immediately preceded it. And the checksum is DC4B, blah, blah, blah. So it has a pointer to the commit that immediately preceded it. And that's how the GUI is able to piece together this history. It just follows that trail of the parents of these different commits. A commit can have one or more parents, depending on the situation. In this case, this commit has one parent. So this commit object also has something called the author. And it's got a guy's name, this guy Oleg, his email address. This right here looks an awful lot like a Unix timestamp. Right? We're at about 1.4 billion seconds after 1970, and then it's got a time zone. It's got another line here called committer. Usually that's the same as the author. There are some cases where it could be different. And then this right here, I suspect that's his commit message. Let's go back and take a look. So again, here's the latest commit in this open source project, and sure enough, that's the commit message. So when we're looking at this in a GUI or in the terminal, what we're really doing is we're asking Git to look at this stuff that's in its object store. And so this is its commit object. So now I want to follow the trail a little bit here. There's something here we kind of glossed over. It refers to something called tree. And it starts with AE. So let's take a look at that. Let's go back into our object store. And there's a folder called AE, and we open that up, and we see more of these files, these sort of nondescript files. And let's look at the rest of it. 8C49. Okay, and it ends, just to double check, with 3C6. So it looks like that commit object that refers to that commit that we're looking at in the repo refers to something called a tree, and it's in this object right here. So let's open that up. And again, we see some garbage. But we kind of suspect that that's maybe compressed data. So let's go into the terminal and use that same utility to expand that out into another text file, and then go back and look at that, and that's this one right here. And so what we just did was we uncompressed that file, and as we can see, this looks an awful lot like a directory, right? So this is really a top-level directory of all the objects that are in Git's object store and where they belong in the working directory at the top level. Now, some of these things, they're blobs. We'll look at that in a second. Some of them point to other trees. Those would correspond to subdirectories that are in the working directory. We've already seen what a tree object looks like. So this looks a lot like some Unix-style permissions. This is a type of object. That's a unique identifier for another object, and that's the name of the file that it corresponds to. And so let's take a look. Let's pick one of these guys, say this one right here. And so we're going to go back into our objects folder. And it was, again, it was D332. So there's D3, go into that. And then it was 32C. And it ended with 9F4. And again, as you might predict, if we open this up directly, we see a bunch of garbage. But we're pretty sure now that that's actually compressed data. And we'll uncompress that and redirect it into another text file so we can take a look at what it really represents. And that's this guy right here. Oh, okay, so this is starting to look familiar now. So this was this blob that corresponded to this grunt file.js, so some JavaScript source code. And here's the source code. This is the entire contents of that file at that point in time where this guy Oleg said, hey, take a snapshot of it and sock it away for me in case I need it again. And that's this right here. Again, it's the complete file. There's no deltas in here. If we look at the commit itself, we look at the changes, he only changed one line of code. And Git went and it grabbed a copy of the entire file. And we can see that for ourselves now. So this kind of explains why Git is so fast, because when you go back and you say, hey, I want to check out this commit or look at a version of a file at some point back in our timeline, all it does is it pulls out its commit object and it sort of follows the trail to the tree that represents what versions of files were in the directory, the working directory at that point, and then it just goes in and grabs those versions of those files as it existed at that point in time. And that explains why it's so fast, because it's just reaching into its object store, grabbing those files and copying them into the working directory. That's why it only took a second to do this. It doesn't care that it's 4,000 commits back. It's just a simple copy operation. It uncompresses the data, and there you go. And that's why Git is so performant. So I want to show you something. This is a document called the Git Community Book. And it's actually a little out of date now. They're not maintaining it anymore. But this is actually the best explanation that I've ever seen as to how Git works underneath the hood. And this is what we were just looking at right here. We have a commit object that represents that commit. It's got metadata about that commit. It's got a pointer to a tree object that represents the top level of the working directory. And then that tree object has pointers to one or more other tree objects that represent subfolders, and then pointers to these blobs, which represent those versions of those files at that point in time. I'm going to give you a link to this, and it's worth looking at just the first chapter, about the first dozen pages or so. And if you do that, it's really going to cement your understanding of what we were talking about. This object store that we were looking at here, this is actually an example of something called content addressable storage. And so I want to show you something, a quote from Linus Torvalds back in 2005 when he had just created Git and he was trying to explain it to people. He said, in many ways you can just see Git as a file system. It's content addressable, and it has a notion of versioning, but I really designed it coming at the problem from the viewpoint of a file system person. Hey, kernels is what I do. And I actually have absolutely zero interest in creating a traditional source code management system. And so now you know the secret. You know what Git really is. Fundamentally, under the hood, Git isn't really a version control system at all, per se, as much as it's really sort of a new kind of file system, this content addressable storage. And yeah, it has layers of version control layered on top of it, but really what it is, the essence of what it is, it's a new type of file system. And so the versions of files are stored based on their content, which is the checksum of each of those files. Now, I just want to show you something else real quick. If we go into this refs directory, refs, this is within the .git folder again. It's got a subfolder called heads. I want to show you one other thing, and this is hopefully going to bring this all home. We've got something called master. Now, we know we have a master branch. That's the timeline that they've been working on in this repository, on this master branch. So what is a branch really? Well, now you know enough to understand really exactly what it is. We're going to open this up in a text editor, and you can see it's just a unique identifier. It's a pointer. It's a pointer 96. Let's go back here. It's a pointer to that commit object that we were just looking at, this guy right here. That's what a branch is. A branch is a pointer to a commit, and because each commit points to the commit before it, you basically have a timeline of a history of all these changes. That's what a branch is. Now, unlike in Subversion, a branch it's something in a different directory if you want to create a branch, quote unquote. The reality is that Subversion doesn't have any notion of branches. It's just a simple little naming convention. You want to create a branch, you take the entire contents of your repository, you copy it into this subfolder called branches. That's a very expensive operation. If you've got a gigabyte's worth of files, you copy it all over. That's another gigabyte's worth of disk space. So it's a bit of a misnomer to say that Git doesn't care about conserving disk space. Actually, it's very efficient at it because any file that has the same content anywhere in the working directory, regardless of what the file name is, it calculates its checksum, it goes to its object store, and it says, oh, wait a minute, I've already got this file. I don't need to store it again, okay? In addition, on top of that, this branch, it's a lightweight reference. It's just a pointer to a commit object. So I want to kind of drive that point home here. I'm going to duplicate this file and go in just for fun and rename it. I'm going to call it dev, okay? And so if we open it up here, we'll see exactly the same contents in that file. It's just a pointer to a commit. I'm going to go back to my GUI and hit refresh, and what do you know? Lo and behold, we just created a branch, because a branch is a lightweight pointer to a commit that in turn points to files that were snapshotted at that point in time, and it also points to a history of other commits. That's what a branch is. It's as simple as that. So we've established that branching is actually a very cheap operation under Git, and so it really becomes a much more useful part of your workflow because you don't have to copy lots of files all over the place. You can just create branches, and there's actually something called Git Flow, which is sort of a best practice that's evolving, which is a set of naming conventions for different branches that are being used for different types of activities within a code base, within a project. But it's a naming convention that just creates these lightweight pointers, which are branches. That's all a branch is, okay? Our goal was to demystify Git and what it really is at a much more basic level, and I hope we succeeded at that. So from here on, as you go on and you learn more about Git and various workflows around it, you'll be seeing stuff about branching techniques and other commands and all that, but you'll know fundamentally what it is that you're really manipulating and what it's really doing underneath the hood. And I think that that'll really help. And that should put you in a much better position than a lot of people to go on in your mastery of Git. This Git community book that I was just talking about, it's an older version, but again, it's one of the best explanations that I've seen for how Git works under the hood. And if you just skim through chapter 1, this one chapter, which is only a dozen or so pages, it really explains this in more detail, and that will really help your understanding of what we've talked about today. But from this point on, I think that you're in a much better position to go to the next step. You'll have a deeper understanding of this now than a lot of people who are actually using Git who started out just sort of memorizing commands. But thank you very much, and enjoy the rest of the code camp. Thank you.